All right, a couple of cool applications with limits that go to infinity. We're looking at infinite series. So just as a quick warm-up here, write the following as fractions. So most of you will be able to tell me that was a quarter. 0.3 repeated, some will know that's a 1/3. And 0.1 repeated, there might be the odd person here that can tell me that's a 1/9. But what about 0.1358 repeated? Can anyone tell me what that is as a fraction? What about 0.45 repeated over and over again? What you're going to find is those aren't so easy, and yeah, probably one or two grabbing a calculator to do trial and error, but what you're going to find is it's very tough to find a fraction that works. So what do we need? We need the formula for the sum of a geometric series. And that formula, if you did take this in grade 11, you might remember the formula. If not, it's right here for you. You don't have to memorize it. Remember, you got cheat sheets. There we go. So there is the formula for the sum of a geometric series. So we can add up however many terms we want. So what about our two situations then? What happens if r is greater than 1 for this formula? So really what I'm asking you to do is we're going to analyze this formula as n goes to infinity. And this is a little bit quicker than the one before, because what happens when the exponent gets very, very big? The only term that has an exponent is this particular r value, r to the exponent n. When it gets huge, so let's say we're looking at r of 2 to the exponent 10 million, gets to be a very, very large number. If you subtract 1, it's meaningless. If you multiply it by a, it's meaningless. You divide by r, basically meaningless. So what we find is that the sum, there's no limit in sight. It goes forever and ever. So you're continually adding, and there's no end in sight. This is what we call no finite value. So there's no numerical number that we can use to express the sum. And more importantly, this represents a divergent series. Divergent series. There's going to be a question on the test that says, are the following divergent or convergent series? So for our partner then in this whole process, where r is between 0 and 1, when we do the limit analysis as n goes to infinity, for a, r to the exponent n minus 1 over r minus 1, what's happening? Well, r is, let's say, a half. It's a fraction. As it gets larger and larger and larger and larger, we have 1/2 to the 1 million, 1/2 to the 1 billion. This term here is now approaching 0. We're getting very close to becoming 0. So it drops out of the equation altogether, and we're left with a multiplied by -1 over r minus 1. And the formula I typically use in this case, or what it reduces down to, is a over 1 minus r. Okay? And that is the formula for the sum of an infinite sequence or series. So that means that if you have a set of numbers that are multiplied, something being multiplied that go on forever, I can still tell you what the sum is. Okay? So therefore, there is a finite value. And we call this a convergent series. And that is because it converges on a particular value. Okay, so let's do some examples here. The point 1, I want to prove to you that this works. So point 1, if I write it as a decimal, so what we want to do is write it as an exact fraction. So this is 0.11111 ... So my first thing is I'm going to start writing these as fractions. So the first term, 0.1, that's just a 1/10, plus the second one, it's in the hundredths column, so it'd be plus 100. The next one would be 1/1000th. So it just makes up a series of numbers that add up to 0.1 repeated. So what's the multiplier here? How do we move from one term to the next? We're multiplying each fraction by 1/10 every time. So I know A is 1/10. A is the first term in a sequence or series. R is the rate that it's increasing by, or decreasing by, in this case, so it'd be 1/10. So the sum, excuse me, of an infinite series is equal to A over 1 minus R. My A value is 1/10. 1 minus my R value, 1/10. Now I just need to simplify. 1 take away 1/10 is 9/10. Flipping, because we don't divide fractions, we multiply by reciprocals. 10 over 9. 10s would cancel. We're left with 1/9. So therefore, 0.1 repeated is equal to 1/9. All right. So some of us already knew that, and you always check your answer with the calculator, but I want to prove to you the process works. So the second example, what will this look like? Well, it's going to be in terms of expanding it out. 2, 3, 4, 4, 4, 4, 4, so on and so forth. Now the 23 doesn't repeat. It's being added on to the infinite series here. So that 23 is going to be 23 over 100 plus that 4 then is going to be over 1,000. The next 4 will be over 10,000. The next 4 is going to be over 100,000, and so on and so forth. And this is where a lot of people mess up. This 23 over 100 is not your A value. It is not part of the series. The series is right here. That's the geometric series. So you got to be very careful here as to what your A and R values are. So A is actually 4 over 1,000. R is 1/10. So I'm going to find the sum of this right here. I'm going to add up all the 4 repeated. Okay, so the infinite formula then is A over 1 minus R. So 4 over 1,000 over 1 minus 1/10. 4 over 1,000 divided by 9/10. Again, we don't divide, we multiply by reciprocal. 1, 2, 3, 10 over 9. 10, we get rid of one of my zeros. So I would have 4 over 900. Now 4 divided by 900 is only the repeated part. So if I want to write 0.234 repeated, 0.234 repeated, I would have to put 23 over 100 plus the repeated 0.444. All right. To get one final fraction, you need to get a common denominator, which is 900. So multiply the 23 by 9, so you get 207, I think, plus 4. So you'd end up with 211 divided by 900 is your answer. So there you go. So 0.23 with the 4 repeated is equal to 211 over 900. And you always check that with the calculator. Okay, just to double check you got it correct. So this process allows us to change repeating decimals that before you weren't able to convert to a fraction into fractions. What are we doing for time here? I want to move on to, let's set this up quick. There's one little change here, and I'll just show it off the start here. So this is 0.14252525. So that means the 14 is being divided by 100. The 25 is being divided by, it's because the 25 is repeating, it won't be by 1,000, it's going to be by 10,000. And it's going to, the zeros are going to increase by 2 every time because we have 2 terms on top. So the next one would be, what do I have there? 4 zeros, so it'd be 6 zeros. So on and so forth. This time your R value is going to be 1/100th because you're going up by 2 decimal places each time. So your A value would be 25 over the 10,000, and your R value is 1/100. Okay? I'll let you try that one, and if I have time, I'll come back and finish it off. The final answer, if you want to check it, therefore 0.1425 repeated, you should get 1,411 over 9,900. And if I have a chance, I'll come back and finish. So just flipping to the last example here. Divergent or convergent, what's the difference? So when you look at it, it's increasing in value. So if I was to ask you, what would the last number be? And if you saw that there was no end in sight, okay, so no end in sight, I guess, so to speak, end in sight, then there'd be no final value here, no limit. No limit. So this is an example of a divergent series. So if you can find that the base is greater than 1, we have a divergent series. All right. In this case, when you're looking at the pattern, and I ask you to predict what's the last number, this time you might be willing to wager a guess, and you'd probably say it's probably going to be 0 because it looks like it's getting closer. So there appears to be a final value. Oops, value. And in this case, it's 0. So therefore, if you can see a final value in sight somewhere, then you are dealing with a convergent. It's converging on what you think it's going to end up with. And that's your difference between divergent and convergent. And so there's the homework. You're going to find it looks worse than it really is because some of them you're just looking at them and just saying convergent or divergent. So don't really have time to go back and finish that up. And if you have any questions or you want me to go through that example that I didn't get a chance to finish, by all means let me know, and we'll do that in class.